Given, 3 strings S1, S2, and S3 of lowercase English letters. Rule: S3 is an interleaving of S1 and S2 if it uses every character from both strings exactly once, without changing the order within S1 or within S2. Output: true if S3 is a valid interleaving, false otherwise. In the first example, we weave S1 and S2 into S3 without breaking either order. Take the first two A's from S1, then DBBC from S2, then BC from S1, then A from S2, and finally C from S1. That spells adpkak, so the answer is true. In the second example, the same S1 and S2 cannot spell S3. After matching adb, S3 wants an annexed, but the only remaining S1 prefix starts with C. The merge breaks, so the answer is false. When you're asked to weave two strings into a third, your immediate instinct is to use simple pointers and match characters greedily. But the moment both source strings offer the exact same character at the same time, a greedy approach is blind. Choosing the wrong string creates a catastrophic butterfly effect, leading to a dead end. If you try to fix this with row recursion by guessing every path, your timeline splits exponentially, crashing your engine. We need a way to explore all paths simultaneously. Here is our massive paradigm shift: we map our problem onto a two-dimensional coordinate system. The horizontal axis tracks how many characters we've consumed from string 1, and the vertical axis tracks how many we've consumed from string 2. Our current position in this grid automatically dictates where we are in string 3, because our current row plus our current column equals our exact index in S3. The entire problem transforms into a pure maze navigation game. Before we can explore the center of our maze, we must establish our baseline borders. We seed the origin at 0, 0, 0 characters taken from string 1 and string 2 means we are at the empty prefix of string 3, so that starting cell is trivially true. The top row represents an alternate reality where we form our target string using only string 1, leaving string 2 completely untouched. We march across this row sequentially. A cell can only be marked true if its left neighbor was valid and the current character of string 1 matches string 3. The moment a single letter mismatches, that entire highway breaks down, and because you can't build a highway past a broken bridge, every remaining cell to the right instantly defaults to false. We run the exact same conditional scan straight down our first column using string 2, locking down our perimeter boundaries. Now, we conquer the center of the maze. To determine if any coordinate square is a reachable reality, we look backward at its two entry gates, our left neighbor and our top neighbor. A path can enter horizontally from the left if that neighbor was valid and the current character of string 1 matches string 3. Alternatively, a path can drop down vertically from above if the current character of string 2 matches string 3. If either gate is open, our current cell becomes a confirmed, reachable stepping stone. With our movement rules established, our pathfinder sweeps across the matrix, systematically unlocking every valid intersection. We don't have to guess or roll back our choices, the matrix naturally tracks all viable realities at the same time. The moment we evaluate the absolute bottom right corner of the grid, we have our answer. If that final cell is lit up true, a valid interleaving path successfully traversed the maze. We unlock our solution in clean, deterministic, linear matrix time. We begin by executing our setup phase. First, read off m and n from the two source strings, and verify that m plus n equals the length of string 3, otherwise interleaving is impossible and we return false immediately. With that guard passed, we allocate a two-dimensional Boolean matrix sized m plus 1 by n plus 1, mapping out a clean 4x4 grid where every intersection represents a distinct substring milestone. We immediately seed our baseline origin at coordinate 0, 0 to true. This represents our mathematical base case, establishing that two empty source strings can successfully interleave to form an empty target string. Next, we lock down our perimeter boundaries, evaluating realities where we use only one source string. We sweep across the top row with string 2 and down the first column with string 1. A boundary cell inherits a true status only if its predecessor was valid and its trailing character aligns perfectly with string 3. The moment our string's characters mismatch our target, that highway violently cuts off, forcing all remaining cells along the border to lock out as false. With our boundaries locked, our nested loops sweep through the interior of the matrix. At every single coordinate intersection, the engine looks backward at its two entry gates, its left neighbor and its top neighbor. A path successfully opens horizontally if the left cell was valid and the current character of string 1 matches string 3. Alternatively, a path drops down vertically if the top cell was valid and string 2 matches string 3. If either gate is open, our current cell becomes a verified stepping stone. Once our loops finish processing every subproblem intersection, we bypass any need for complex recursive backtracking. The entire history of all viable paths has already accumulated right here on the board. We zoom straight into the absolute bottom right corner cell of our matrix, extract its pre-calculated Boolean value, and instantly return it to conclude our interleaving calculation. One final space optimization: when we advance row by row, each cell only reads the strip to its left and the cell just before it in the same row. We never need the full matrix in memory, a single Boolean array of length n+1 is enough. Overwrite that array for every row of string 1, and auxiliary space drops from order m times n down to order n. Let m and n be the lengths of strings 1 and 2. Time is O of m times n. The nested loops visit every DP cell once with constant work per cell. For space, the straightforward version keeps the full two-dimensional Boolean table, using O of m times n memory. We can compress that to O of n with one rolling row, because each new row only needs values from the row above and the cell to its left. Two-dimensional version: allocate an m+1 by n+1 Boolean table, seed the borders, fill every interior cell from its left and top neighbors, and return the bottom right answer. One-dimensional version: keep a single Boolean array of length n+1. Seed the first row, then overwrite that array for each row of string 1, reusing the old cell as top and the left neighbor in the same pass.